This part describes the speed and distance measurement system, the MP3 sound source, and the synchronized chuff system. The audio signal mixer and power amplifier are also described. I will start with the speed system. The speed and distance measurements make use of a cycle computer. The cycle computer has its own CA3120 coin cell power supply, and I decided to retain this. It would normally operate from a reed relay and a magnet on a bicycle wheel, but here it derives a signal from an incremental encoder geared off one of the tender wheels. The encoder has differential of RS422 outputs, but I used it single-ended. The 1 pulse per rev logic signal is high for 90 degrees of encoder rotation, that's 25%. It can easily drive an opto-isolator via a 1K resistor, and the cycle computer works OK with this longer length of pulse. It was simply a matter of cutting the cable and interfacing it via the opto-isolator. This diagram shows the circuit between the encoder and the cycle computer in the hand controller. The encoder 1000 pulse per rev output was originally going to be used to feed a data logger, but that idea was scrapped. It would have been convenient to remove the encoder and take the pulse signal from the chuff synchronizer, but the cabling was already in place and would not support this. The gear ratio and tender wheel diameter result in an effective wheel circumference of 55 mm. Entering this value into the cycle computer gives the correct scaling. I was surprised that the cycle computer could accept such a low value. The computer was then set to give results in kilometers per hour and kilometers distance, which gave more resolution than MPH. At 10 kilometers per hour, the encoder's single pulse frequency works out as 50 Hz. This photo shows a simulation with a generated frequency of 50 Hz displaying correctly as 10 kilometers per hour. The pulse width modulating unit was set up at 25% to mimic the encoder. I will now describe the chuff system. I was interested to see if I could produce a reasonably realistic sound of the steam exiting the cylinders synchronous to the piston position. The first decision was to use the same sprocket size for the centre axle and the sprocket in the gearbox. Since the gearbox shaft therefore moved in synchronism, I was able to fit an aligned 4-arm sector to it and use a slot-type optosensor to set the start and duration for the sound. Initially I experimented with recorded sounds, but then decided that white noise was a good approximation. This diagram shows the final circuit that I decided upon. Zener diodes are well known as noisy devices, so I passed a small current through a 10-volt Zener and followed it by a 2-stage amplifier and bandpass filter. Since I was not interested in hi-fi, I then fed this to an efficient digital speaker amplifier via an electronic switch controlled by the optosensor and the mixer circuit. The hiss was okay, but the starts and ends were too abrupt. To smooth these out, I experimented with one of the channels of a CMOS CD4016 FET switch and achieved a result which I considered acceptable. The CD4016 is a 4-channel CMOS analog or digital switch, normally commanded abruptly on and off by means of an input logic signal. However, I discovered that if this logic signal is applied gradually via a resistor-capacitor network, progressive soft switching occurs. The CD4016 is supplied from plus and minus 5 volts. The analog signal must never exceed these values, so the previous op-amp is followed by an attenuator to avoid this. In the off state, the CD4016 has virtually infinite resistance, and in the fully on state, a resistance of just under 300 ohms. This photo shows the inside of the sound unit that I built. On the right is a D connector, which receives the signals and power source from the locomotive. Next comes the white noise generator and soft switching board. The middle board is the eBay digital amplifier which I bought for the amazing price of £1.53 delivered from China. The left-hand board is a simple single-stage mixer. The front panel has two volume controls, one for the chuffs and one for the MP3 sounds from the hand controller. There's also a supply switch and a mute switch, which is useful to avoid large clicks from the supply switch. This clip demonstrates the chuff system in operation. A square wave function generator is used to simulate the chuff synchronizer. In addition to the chuff system, I decided to provide recorded sounds that could be controlled by push buttons on the hand controller. To hold the recorded sounds, I bought an eBay MP3 module that takes a removable SD card. The sound can then be recorded as files on a PC from non-royalty sources or visits to a real 9F in action. I decided to make up to 8 sounds available, each of which can be selected by its dedicated button on the hand controller. The sounds then pass via the tender and local wiring to the second channel of the amplifier mixer. The MP3 unit has several operating modes available. It can be set to play to the end of a file or stop when the button is released. It can also be set to allow a second file to halt the previous file. For test purposes, I connected the hand controller directly to the sound unit via some temporary test wiring. The MP3 player runs on 5 volts, which is normally regulated down from the plus 15 supplied by the control card for the demand pot circuit. Since for this test the control card is not present, the voltage is borrowed from the sound system power supply via a test hook. Here are some non-9F test sounds.
Des tas de citoyens amoureux de la nature et qui n'ont pas les moyens de voyager. Ils ne connaissent seulement...
If anyone knows of some suitable royalty-free sounds, I'd be glad to hear. I used the music track to check the quality of the system. There's also a miniature jack output on the MP3 module for test monitoring with headphones. This photo shows the completed sound system with its power supply. It's worth looking at the power supply. I wanted it to be able to operate either from the 12 volt or 24 volt main battery as fitted. The supply is switched to an eBay buck boost converter that can operate from an input of 3 volts to 32 volts and provide an output from 5 volts to 35 volts. This output is set to plus 12 volts, which is suitable for the digital amplifier. The switched supply also drives a plus 9 volt to plus 36 volt Traco converter that provides plus 15 and minus 15 for the white noise generator and the mixer. Plus 5 volts and minus 5 volts are regulated down from the Traco to supply the soft switch circuit. The sound system will sit in the boiler near the front. It will probably be fitted between aluminium guides glued in place with epoxy resin and be secured with neodymium magnets. Part 6 will cover the testing of the complete loco tender system and will partly take place on my test track. There will be a delay until I can get this organised.